Hi. So now we're going to talk about some of the really, really basic chemistry of life. So we're not going to get very detailed in this conversation, so don't freak out in case you haven't had good experiences with learning chemistry in the past. So this is pretty straightforward and makes a lot of sense if you just think about it. The problem with chemistry, and in with cells as well, is that you can't see these things, so it's harder to relate to them. But it's really very, very important for us to get this. As I say here, what characteristics of life are most directly dealing with chemistry? Well, really metabolism, because the dry definition of metabolism is the sum of all chemical reactions in the body. So here again, you have your learning outcomes. What am I supposed to get out of this? And we're really going to look at this idea of explaining interrelationships among molecular, cellular, tissue, and organ functions in each system, and the causes and effects of homeostatic imbalances. All right, because almost often these imbalances, if not always, come down to some chemical, some again hormone, ions, so forth that they've been disruptive or they've been disrupted. And I say here that now you understand that disease results when homeostasis cannot be achieved, right? You can't return to balance, and the cause of the imbalances are basically molecular, right? Have to do with molecules. And we can state that here, right, the disease is based in the chemical field, and to understand that, we have to have some understanding of chemistry. All right, so there's my plug, and I hope you're going to be okay. So we start off just by defining some of the language of chemistry, elements and atoms, which are structures of matter. So what is matter? Well, it's anything that takes up space and has mass. I know, wow, that's so. I often say to students, so tell me what isn't matter. That might be easier. Now, technically, we debate about whether or not energy, but that's about the only thing we really consider not matter. Energy is associated with matter. Right? So that's really what we're still looking at in this chapter, and I told you energy is a very central theme as well. And the way we capture and transfer energy is in biochemical pathways we call metabolism. All right, an element cannot be created or broken down by ordinary chemistry. All right, so in other words, it's the smallest we can get in the process of degrading things, right? So you still have the elements around. They don't fall apart into their electrons, protons, and neutrons. And you don't make these, right? They actually come from the Earth's crust. They formed as the Earth formed. They are often called minerals, right? So if you talk about getting your vitamins and minerals, we're talking about in the minerals your elements. And yes, they are absolutely required. And they're going to be used to make the larger molecules, right? And then some of them are going to stay pretty small, like sodium, potassium, calcium, and in their ionic form, and won't actually combine into large, in the blood at least, won't combine into large molecules. So this table and this graphic here really nicely shows that you are actually technically mostly oxygen, and then next is carbon, hydrogens, right? Nitrogens, calcium because of your bones, right? Phosphorus because of your bones, right? Potassium, right? Sulfur is going to be associated with protein as well, okay? And I focus on the sulfur, the nitrogen, the oxygen, the carbon, hydrogen, and phosphorus as key components, because these are going to be used to make the molecules of life known as protein and carbohydrates, lipids, and nucleic acids. So about 95% of you is, and you see this right here as we look at this, is again carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. All right, so atoms are, we can just represent them here in a cartoon like this. This is helium, one of our noble gases. It's inert. It doesn't tend to be reactive because it's very, very stable. And so we talk about this, again, it looks kind of like the solar system here. There's a central area, and the irony is, of course, the sun is one big fusion reaction making helium all the time. And these electrons, smaller smaller bits of matter moving around this large central bit of matter. So they're the smallest quantity. So atom is a unit, right, of an element. And it's going to be, an atom will have this, so an atom of helium has the properties of the element. And this is where we start to build. We start with the atoms. What are the three particles which most every atom contains? Well, they have to contain electrons, protons, and neutrons. Okay? And these nice cartoons show us how they arrange themselves. So these, yes, are still organized. An atom is not alive. Again, it's a unit of matter, not a unit of life. But it's still got to be organized in order for us to make something with it. And it turns out that the protons and neutrons that are found in the middle, that we call the nucleus, are much, much larger than the electrons, which are very small and are moving around. And this organization comes about because of the charges. The charges are very important. So positive protons, right, negative electrons. And then neutrons are, in fact, neutral. And this attraction by opposite charges helps to organize. And of course there's repulsion by the positive, which is what limits some of the, and helps with the formation of the atoms. All right, so atomic number and mass, very, very simple principles that tell us about these atoms and what they are capable of doing, how we're going to build with them. So your atomic number is basically the number of protons. Now, let's stop here a second and state that the atomic number is unique for every element, right? So if you add more than, here's 3 here in the element lithium, and if you added a 4th, right, you would have a different element. And if you took away a proton, you'd go back to helium, right, which has 2. So that's a unique characteristic. There's only one element that has 3 protons, and that would be lithium. Okay. Now, atoms are also characterized as electrically neutral, which means that if you have 3 positive charges, you have to have 3 negative charges. And that is indeed the case. If there's an imbalance in these numbers, then there's a charge, right? So if there's more protons, the atom is positive. If there's more electrons, it's negative. So we consider, for the most part, that atoms are neutrally charged, and so there's 3 positive, 3 negative, okay? And again, like we said before, the electrons are much smaller, and they are moving around this cluster of protons and neutrons. So what is the mass then? Which is, again, you don't need a whole lot to describe these elements. They're very simple things. But the mass, right, is then the number of protons and the number of neutrons. So while lithium's atomic number is 3, its atomic mass is 7, because you add all these up. There's 7 things here. We don't count in the electrons because they're so small. They do not add much to the mass of the atom. So again, when we give you the number and mass, these are unique features, especially the number, right, for these atoms. They describe something very important, though, for us and help us to figure out, how these atoms are going to combine together to form molecules. All right. So atomic number says, hypothetically, could 2 different elements have the same number? And we've already answered, no, they can't. Mass number, right? The mass number, or atomic mass, as we call it, the same thing here, is basically this idea, again, we're going to add now the neutrons, right? And so the mass number for lithium here is 7. And I've already mentioned atoms are electrically neutral, so this means we have a balance of electrons with protons, same number. All right, this is a periodic table, and these elements have actually been named. They weren't named at the time of this publication, but they have been named. But it really doesn't matter to you guys, because when we're addressing the life sciences, we really only go up to about 20. Oh yeah, we have these. You have iron, right, and manganese and chromium and cobalt and so forth. You have a lot, and copper and zinc. You have a lot of different elements in your body, but the majority, as we looked at that first table and that diagram, are the first 20. So we're really going to focus on the first 20. And I said, and then we're going to narrow it down even further and focus on carbon, nitrogen, oxygen, phosphorus, sulfur, and hydrogen. Okay? And they're in the first 3, right, rows of the periodic table, right? And very, very close together. So the periodic table was really it was created by Mendeleev, and it's a really very well organized and gives you a lot of information. If you didn't realize it, it turns out that the rows tell you how many orbitals an atom has, and orbitals, of course, are the electrons or shells. So you see here lithium has 2, and you'll notice that it's in the second row, right? So that's telling us already, without looking or knowing anything else, how many orbitals or shells that atom has. And then the grouping is really there to describe how many electrons are going to be in the outermost orbital or shell. So Mendeleev was very clever, and he does a huge favor in creating this scheme that looks kind of odd to some people, but it's totally appropriate and really helps us know a lot and understand a lot about chemistry just at a glance. Okay, so isotopes. What does iso mean? Iso refers to that word root, that prefix is equal. So something is equal. So what is an isotope? All right. Well, an isotope is going to be 2 of the same atom. So protons, same number of protons, same atomic number, but different. And that's where the same is, equal or same. But they have different numbers of neutrons. Okay. And so here I give you the classic example of C12, C13, C14. And if we go back to the periodic table, we realize, oh, here's carbon. It's got 6 protons. That's its atomic number. And here is its atomic mass, or mass number, is 12. So if I do my math right, it means that carbon has 6, right? Because 12 minus 6 is 6 neutrons. All right, so most of the atoms of carbon on the planet will have 6. But some of them have 7 and some of them have 8. If I just do the simple math here. All right, so these are all the same element, right? They have the same number of protons, same atomic number, but they have different numbers of neutrons, right? So atomic numbers is the same basic function, right? You can use this carbon and this carbon to build just like you can this carbon, all right? Their atomic weights or mass are different because they have additional neutrons, all right? These are considered unstable. All right, and though they're naturally occurring, they are unstable, and so they exhibit some degree of radioactivity, which means they are releasing energy, right, that we can measure. So they emit subatomic particles. And if you recall if you read the description of positron emission, you would see that, that of course, along with some of the other imaging techniques, are dependent upon this radioactivity to assess a problem or diagnose a problem. So unstable isotopes are generally unstable, and some more than others, and they are decaying, which means they're releasing some subatomic particles which can be captured on films and other medium. All right, so it's the behavior of the electrons we really want to focus on as we move forward. So here in this last slide of this video, I'm going to say, atoms are not isolated, they're going to interact, all right? And I said we have all kinds of chemical reactions going on that we collectively call metabolism. And it's the electrons which are basically responsible for the bonding. How are these atoms going to get together? And so I say here there are 1 to 5 electron shells, and we're really only dealing with things up to 3 and in this class, right? And they can hold 8 electrons. That's the maximum number that an outer shell can hold. And since 8 is an octet, we talk about this as the octet rule. The only exception is shell number 1, which only holds 2 electrons, and we see that here. Helium is stable. We can't put any more in there. 2 here as well. The factor which determines whether an atom is going to react and how it will is the number of electrons in that outer shell, and we call it the valence.